Hello again, folks. Today we're going to be starting with, I'm just doing this weirdly now, chapter 5, all right, and we're going to be doing specifically sections 5.1 and 5.2. As you can see on the calendar, today is the 22nd of October, section 5.1, 5.2, we're right on target. All right. I think next week, just judging from the material, I might move 5.4 to this day. But I'm still kind of debating it. There's kind of a lot, and it's pretty involved, so I might just move one of these things over to that Thursday, but I'll let you know at that time. Anyhow, we're starting fresh, so if you are inclined to separate out any partition your notes, all right, the material that starts today is building towards the next test, okay? The older material will always be relevant somehow as foundational information, but chapter 5 is what is the beginning of test number 2 in theory. Okay, so let's get started with, let me complete this thought. The packet has a lot of stuff this time. All right. This is the top page basically. All right, so look for this in Canvas Canvas pages. I'll have the link for you in announcements. All right. This is key features of a quadratic function. There's a rundown of some key sequences, if you're using your calculator, and I encourage you to do that for the same purpose. You have this sheet already, but it would probably be to your benefit. If you haven't printed it yet, I would. All right, as I've mentioned, we're going to be going through these toolkit functions, right? Everything but exponential and logarithmic, because that's later in the book, all right? So right now we're discussing square function, all right, essentially. This is the basis of a quadratic, all right? And eventually we'll get to rational functions, the basis of which is the reciprocal function, okay? What's really useful about this is the domains and the ranges are written underneath, right? These are, not transformed at all, but this is still useful, right? Right, the domains and ranges. There's a sheet I had made. This is a word bank. I'm going to walk you through this a little bit later when we get to section 5.2. And another thing, just for the sake of clarity, how you would classify the degree of an individual term or the degree of a polynomial. Okay. Try to print those. In color, ideally, right? If you have the ink. It's expensive. Actually, boarding the other day was like $70. I kid you not. Couldn't believe it. And that was at Walmart, too. Right? Just blew my mind. Anyhow, have your calculator on handy too, because I'll show you how to use that. Certain features. Now we'll get started. I'm running a little late today, so let's see how dark it gets. It's not quite 2 o'clock yet, but it's very gray today. Open the window, listen the air in here. Alright, let me start with this. Alright, section 5.1 of these two is about quadratic functions. Get down, get funky. Alright. I like to draw these sort of family trees, if you will, to give you an idea of where we are in math space, if you will. Alright, so we are on the subject of functions. And it sounds like there's a printer. Every day I hear noises out my window. Late at night, sometimes like 3 in the morning, and it sounds like an air raid siren. Right? And if not that, it sounds like a prison break. Anyhow, in the subject of algebra, or in the subject of functions, I should say, there are basically 2 categories. There are algebraic functions, and then there's this other category which will be important later, which are called transcendental functions. It's funny, when you stand next to something, your ability to spell just goes right down the toilet. Right. Transcendental, right? What are transcendental functions? The exponential, logarithmic, and trig functions, essentially, right? That's in our future, right? So it's not immediately important. And you could just think of them as basically being non-algebraic for all intents and purposes. Okay, transcendental sounds so much nicer though. Anyway, of the algebraic functions, right, there's the ones that are relevant to us immediately now, which are those that are polynomial based. And if this is fading out, I will get another blue. Hopefully I have another blue. Right. Polynomial functions, of which quadratic is one type. Let that think about itself. Okay. And then there are two others which again are not immediately important to us, but we have actually dealt with them. There's linear, which we are familiar with. Ow, pardon me, I'm putting this in the wrong place. Shame, shame. There's rational, which is going to be coming later in this chapter. And then there is radical functions in theory. A polynomial function is something that is based upon this building block. Something that looks like this. Think of this as being the smallest Lego in the box. You know, the single dot flat piece, if you will. And there's some key features here. I mean, this coefficient up on the front has to be real, and this has to be non-negative, right? But it could be some sum of difference of these, or just one of them. Right. Of the polynomials that we have discussed, we have discussed the linear type of function. Right. The identity is a specific type of that. It's the most slimmed down, dumbed down version of it. Right. Then there's the square function. Which is more closely related to this. All right. I'm always debating whether I should put this at the top or vice versa. The quadratic, which is based upon the square function. And then in theory there's cubics as well. Running out of space here. Anyhow, where are we in this family tree? Right now we're here, right? The quadratic type, right? So basically we're going to have a 2 sitting in the position of the non-negative exponent, right? The degree. Right. Now, what I'll do is I'll just sort of write something about this under quadratic, but I need the board space. So what I'm going to do is I'm just going to have you, if you want to make this drawing as well for reference, just put 3 legs on quadratic, and then I'm going to give you some more information after I erase this. This is not enough space. Okay. Let's see. Quadratic is sort of an amped up version of a square function. The square function is just y equals x squared, or function of x equals x squared, whichever you prefer. Then the quadratic function is usually, it's usually a trinomial. Right? Usually. Right. So it's something more sophisticated looking. There's, as I mentioned, 3 sort of incarnations of this, right? There's kind of the usual way, right, which we call the general form. You would see it. And then there is the standard form. And there is, in theory, another classification which you're not immediately responsible for. The intercept form. Being that you have a graphing calculator, these are not, it's not important to have to memorize them. I want to make you graph them by hand, a couple of them, just so you get a better feel for it. But yes, you would use your calculator. All right. These two are the two that are immediately important. All right. This is a nice option, particularly if you're not using a calculator. All right. Anyhow, how does this look? All right. It looks like this. The function of x, if I'm sticking with function notation, is ax squared plus bx plus c. All right. Notice it's a trinomial. Its leading term here is degree 2. All right, because it's really square. The standard form looks like this. I'm going to just stick with the function notation. A x minus h squared plus k. That probably looks remarkably similar to the transformation model. There's no coincidence there. The intercept form would in theory look like this. And don't be intimidated by the choice of letters in it. It's really just a matter of preference. If you're wondering, geez, where did the letter P and the letter Q come from? It's just to fill a void that this is some number and this is some other number. Okay? That's distinct from the x's. What's important is what is happening in this sort of evolution here. This is apparently not factored. Right. It's the most familiar, perhaps. It looks like a quadratic equation, but it's not factored. All right. This is something that is partially factored, obviously. And why do I say that? Because there's evidently a parentheses in it, right? And a coefficient up in front of the parentheses. This is completely factored. Now there's some advantages and disadvantages here. Let me see if I can separate this without getting myself in too much trouble here. There's always a lack of real estate for me to write. The advantage really, if you were going to start graphing by hand, would be either the standard form or the intercept form. Right? They give you different pieces of information though. The standard form here basically is partially factored to reveal the vertex. H comma k of the graph. Now, I guess one thing I should mention ahead of time is, well, if you have something that is a square function, how does that look? This is the most basic square function, right? Something that is that shape, all right? Goes through the origin, goes through the point 1, 1, goes through the point -1, 1. And it has that unique, distinct shape, all right? This is the most familiar, and it basically yields a parabola. What's true about parabolas, though? Parabolas have a vertex, an inflection point, alternatively, right, which is the lowest point of the parabola usually, right, unless it happens to be upside down, in which case it's a maximum, right, instead of a minimum. Anyhow, if you're trying to draw something, remember, if it was a line, you need 2 dots, right? If it's a parabola, ideally, you would need 3 dots in order to draw a satisfying picture to flesh out the skeleton, right? And knowing where the vertex is can help you do that, right? If you have something partially factored in this arrangement, the number sitting here and the number sitting here, all right, is in fact the vertex of the parabola. So that's the advantage of having this, right? There's other features, again, as I mentioned. This resembles, right, the transformation model, right? F of x is equal to plus or minus a times dx minus h plus k. What are some distinctions here? Well, in this instance, there isn't an obvious horizontal stretch here, right? But there would be a coefficient out in the front here, which would make a vertical stretch, right? Make it a little bit narrower, perhaps, or a little bit more squat, depending upon whether it's a stretch or a compression, whether this is a whole number or whether this is a fraction, say. A positive or a negative would just reflect it vertically, right? And there would be shifts, right? So the inflection point, or in this case, the vertex, would be revealed in this shape. And you kind of like it for that reason, right? If you want the whole 9 yards, if you completely factored something and you had it in intercept form, the advantage of that is that it would reveal the x-intercepts. And if we're talking about a parabola, because of the shape of a parabola being what it is, this sort of hybrid U-V shape, it's neither of those things, but it kind of resembles both of them, as if it was the I hate to say this, the bastard child, all right, of a V and a U, all right. It might have, not in this particular drawing here, but it might have 2 x-intercepts. That's usually the norm, all right. They are referred to as zeros. Right. We went through the trouble, and I think it was at least, if not chapter 3, then it was definitely chapter 2, where we went through the process of factoring stuff and then using the zero product rule. Well, if you just called this y, all right, and then called it 0 specifically, then it would be an instance of something that's factored set equal to 0, and the zero product rule would be useful, right? That's really the whole point of that. Anyhow, the x-intercepts would be revealed here and here, all right? You just have to reverse the signs. Okay, so in theory you have these choices. Just as a sort of technicality here, all right, it's a little frustrating because the nomenclature has not been agreed to. Notice that this is called the general form, right? It's the general form of a quadratic function, right? These are functions. But if it were just an equation, not a function per se, then we would call it standard in this instance, right? That's why I kind of like the alternative name for this, just not to confuse anyone. This is sometimes called the vertex form. Right? I think that's better labeling, personally, rather than shift over the name to something else, just because it's not just an equation now, it's a function instead. Right? It's confusing. All right? So, let's go on here. Let me walk you through this sheet now. Okay. Now green, go away. I'll point at this. If you're given something that happens to be in the vertex, aka standard form, right? When you're looking for the vertex, It's just whatever number is sitting here in the parentheses and whatever number is sitting here in the parentheses. If you're given something in general form, there's formulas you could use, right? And this would be it, right? It's kind of similar in the sense of quadratic formula. You know how in quadratic formula you're looking for a, b, and whatever the c value is, and then you put it in the quadratic formula to figure out what x is. When you're looking for a vertex, it's much simpler, right? It's negative b over 2a. And then you substitute that back into the function to figure out what the y is. That's the easiest thing to do. There is in fact another formula for just getting y independently, but it's more trouble than it's worth. Anyhow, here's some features. Right? The quadratic produces a parabola, right, which is kind of a UV hybrid, as I mentioned. Right? If the coefficient up in the front is a positive, then it would open up, and if it's negative, then it would open down. Let me give you an example. We'll graph this by hand. Pull out the thing here. And hopefully this will not fall off the ledge today. I hate when that happens. That looks like it's cooperating. Good. We will try to graph. What's this? Put this out of the way first. Take out a piece of graph paper if you need it. We're going to try to graph this by hand, and then I'll show you how to use your calculator. All right. The function is 3 times x plus 1 squared minus 3. Again, there is no coincidence. This resembles the model that we're familiar with, the transformation model. This is an A, right, from the model. Right? This is the H value, right? And this would be the K value. Right? In the case of transformations, we just generalize them as, oh, it's a horizontal shift and a vertical shift, right? And this is some kind of stretch or compression. But in this case, because we're dealing with something that's quadratic, you could tell that that's the vertex right off the bat. I don't want to jump the gun, all right? So let me just sort of walk you through these features. I'll put this over here. Let's kind of think about this as being rule 0, if you will. Right. What is the degree of this? It's a degree 2. Since it's a degree 2, it's going to produce the parabola shape. All right, something that vaguely looks like this. Now I'll get into this. All right. If A, right, is equal to positive number, and it is, right? This is technically a positive 3, right? It's not written, so one would assume that. Right? This means that the parabola opens up. In the parlance of transformations, we would say that it is not vertically reflected, right? As if it was shifted this way. It's in the normal orientation upward, like so. Yeah. Anyhow, opens up. It, I kind of like to think of it as something like a flower. You could say blooms, right, rather than wilts. Okay. 2. If A is equal to positive 3, and it's really the digit in this case, that's important, right? Just as in the case of transformations, when A is greater than 1, and that's certainly greater than 1, this is a 3 here, right? That means that there will be a vertical stretch. What does that mean realistically in terms of a parabola? It means it's going to look narrower than normal. Right? It will be stretched this way. Right? That's our prediction about that. Now as for 3, it's in the standard form. And since it's in the standard form, all right, we're going to go with basically this sort of formula, if you will, all right, where the vertex is. The vertex is at the location such and such, comma, such and such. Remember, it's unfortunately counterintuitive when it comes to the h value. Right, so if you see a positive 1 here, just realize it is really a negative 1. Right? Thankfully, the k is just intuitive. Right, so it's -3. It's the only thing that I would say is really annoying about this. We could, if we want to, immediately at this point start fleshing out the drawing. Right? I'm kind of tempted to do that, so maybe I will. I don't want to erase this, I just want to start building up the picture. So I'll just cover this momentarily. Alright, and if you printed out the prefab graphing paper that I have, you don't need to do what I'm doing right now, which is draw axes. Alright, I don't know about the full. Okay. So, -1, -3. From the origin, -1 is here, -3 would be 1, 2, 3. We already have 1 dot, right? Being that this is a parabola, again, we ideally need 2 more dots, right? That's just a minimum to draw a picture. Right? This is the vertex, -1, -3. You don't have to label it, but it might help if you've never done this before. You know what that point is. Here's the next thing. If this is, I'm going to just kind of tuck it in here for a moment, right? If the vertex is -1, -3, and it is, right? That means that there's an axis of symmetry, right? Sort of the hinge or the mirror, if you like, all right, that goes through the x value. So x -1. What I would do now is very lightly draw a dashed line, all right? And that will help you draw the picture in a couple of steps. Let me get a ruler. And I'll put this in green, and hopefully it will cooperate. Let's see. Doesn't have to be solid line, just need something to help sort of say that's the middle, if you will. All right. This is the axis of sim. Okay. I've always loved this about math. I have to be perfectly straight with you. When I was in high school, I was more or less indifferent to the subject, but what sort of made the light bulb go off in my head was when somebody said, "Hey, look, you can draw pictures," and I like to cartoon. So that was the hook, you know. Sometimes you just gotta find how it's useful to you personally. All right. Anyhow, so we have our axis of symmetry through the x value, which is the vertex value, x. Let me put this aside now. We need some more dots to flesh out the skeleton here. So, and I'm probably gonna need more space. So what I'm gonna do is maybe erase a little bit now, right? And if I can help it, I'll try to finagle it. Let's see. My lack of real estate here, all right? Step 5, all right? This is basically looking for the x-intercepts. Now you know how to do this. This is all hat to you, right? How do you get x-intercepts? You stick a 0 where there's a y. If it's in function notation, just call this y. And then put a 0 there. And then and then rearrange the pieces. Right? In some instances, it may take factoring, additional factoring, more than what's there. And in other cases, and in this case, it's not going to be too much. Right? So what you would have here is, we're going to call this function 0 in place of y in place of f of x. And then all of these other features. So you have 3x plus 1 squared minus 3. We have to isolate the x in order to solve for x, so we're going to move the stuff around it. How do we do that? Make a little table, right? Start by moving the 3 from here to here. Via opposite operations, it cancels. You add 3. That means on this side you got 3 equals 3 times this leftover x plus 1 squared. Since this is in factored form, it's understood that these two things pressed together being multiplied. If I want to now move 3, I could divide by 3. Both these sides will be technically 1 each, which means that this is now really x plus 1 squared is equal to 1. Now remember from chapter 2, technique, right? When you have something that is squared, in order to basically dismiss these parentheses as the grouping, you would perform the opposite operation naturally. The opposite of adding is subtracting. The opposite of multiplying is dividing. What's the opposite of squaring? Square root, right? And you could get away with that just provided you do it to both sides, right? The effect is that this is canceled, right? And that rips the roof off, and now you have this. X plus 1 equals the outcome of the square root of 1, which, bear in mind, could be a positive, could be a negative 1, which is to our advantage. Remember, we're talking about x-intercepts here, so potentially we'll have 2. There are weird cases where there isn't 1. You'll see that in a little bit. Kind of do the work over here. Right? If you have x plus 1 is equal to positive 1, and in the situation we have x plus 1 is equal to negative 1. If I subtract, sorry for the mess, minus 1 here and minus 1 here, then x is equal to 0. Save that. If I subtract 1 here and subtract 1 here, in this case they're going to amplify rather than cancel out of existence. X is going to be equal to negative 2. These are ordered pairs really, because I use 0 for the y. So what does that mean? Just simply for the lack of space, I'm going to erase this here. We have 2 dots. We have a dot at 0, 0. And we have a second dot at negative 2, 0. Right? Thankfully, we could use that to our advantage and flesh out the drawing. So I'm going to take the graph paper back, put it here. All right. Just to give it some distinction here, I'll put a dot at this location. 0, 0, which is the origin. I kind of slipped this slightly, so I'll move that. This is 0, 0. It is an x-intercept, one of the 2 in this case. And then there's a negative 2, 0. So there would be 1 here as well. It's very skinny already. You can see this drawing. Okay. You could, being that, I don't want to jump the gun, that this is already going through the y-axis, you could pretty much draw a picture right now and you're done. Right? I want to just show you step 6 because sometimes it's not obvious. Right. So let me move this. If you go all the whole 9 yards and you're looking for the y-intercept, let's call that step 6, right? you know how to get a y-int. This is all that. To anyone that has done linear equations, you know you're basically sticking 0 where there's an x. And that is even easier, right? The only adjustment you need to make is stray a little from the function notation. Call this y is equal to 3x plus 1 squared minus 3. And in place of the x's specifically, that one, you put a 0 there, which will make the work much easier anyhow. So 0 plus 1 would just reduce this to 3 times 1 squared minus 3. If you had the choice between multiplying, squaring, and amped up form of multiplication minus 3, you do this first. Do remember these parentheses, it's just in case there's a negative, you have to be careful. The exponent would affect that negative. This is really just 3 times 1 minus 3. This is multiplication first, 3 times 3, 3 minus 3. That means that this is just 0 itself. When x is 0, y is 0. We already know that really, but that's just dumb luck, right? Where's the y-intercept? At the origin. So you would go about your business, right? If it was a distinct point, a point other than what it is established already, 0, 0 is coincidentally a y-intercept, then you would, put it where it is appropriate. Anyhow, this is sufficient in terms of our drawing, right? What should be the case is that, and this is the real point of the axis of symmetry, if you figured out points higher up, and it would just be a matter of inserting an x and spitting out a y, like a little machine. If you figure out 1, right, you could always use the axis of symmetry to count over that many spaces, just hypothetically, all right? It would be, if it was 2 blocks this way, then it would be 2 blocks this way to the parabola. All right, I didn't do the calculation, I only lazily did these 3 points. But that's the purpose of the axis of symmetry, trying to figure out 1, do the mirror image on the opposite side. Okay, all right, let's try the other type. I'll get rid of this. Every time. Get rid of that. I gotta get a beefier ledge here so that it doesn't keep doing that to me. This easel basically has been in my family for a long time. This was my father's drafting table, and then my brother put the piece of plywood on it for me, and then I shortened it and put wheels on it and gave it to my younger sister, and then I repossessed it. So this thing, it's an heirloom is what I'm getting at. I've just only more recently done this to it just for the sake of having a ledge. It needs improvement though. All right, let us say that we are going to graph by hand this second quadratic. And this one, you'll notice a distinction. F of x is equal to x squared plus 4x plus 6. And again, this resembles what we normally refer to as standard form of an equation, but it's called the general form of a quadratic function in this case because it's a function. There's an a, a b, and a c potentially that would be relevant to us. Now, a couple of things. Again, if we were going through the process of deciding by hand, how this should look, let's call this the unofficial rule 0. What is the degree? Right? It's degree 2 again, so it would be the parabola shape because that's what square function does. Right? This is degree 2. So we would have a picture that looks basically like this somehow. Right? Then the actual rules that I have posted here. Right? the A value is equal to a positive. All right, once again, it is not written, so it would, in theory, if it's not written, you would assume it is a positive 1 here, right? And that's sitting in the A position. So since this is a positive, all right, this again opens up, which is more or less normal. We might say it blooms rather than wilts. Okay. 2. A is equal to 1 in this case. And we're paying attention to the digit in this case. This means that if A is exactly equal to 1, it is neither narrower nor wider than usual. That's basically how a parabola would look unmolested. All right. 3. We are in the general form in this case. Right. Therefore, we have to get the vertex via a formula. That is that the x value, firstly, is equal to negative b over 2a. Not too complicated, right? It's pretty short. Right. Where did I get that from? Again, on the sheet. Right? If you decide that you're in the general form of quadratic function, then unfortunately you're going to have to dig a little bit. You use this formula to get the x. So we pluck out what is b and what is a. Right? This is the b, this is what a would be. Let's see, so in place of this I'm going to put a little parentheses and then insert 4. Like a little pocket, if you will. In place of A, I'm going to insert 1. It might be overkill, but I only do that as a good habit to avoid, just in case there's a negative. You don't want to confuse the negative that happens to be in a number with the negative that's in the formula. This is realistically negative 4 over 2. Right? And if you simplify that, this would be negative 2. That's the x value. If you want to get the y value, the easiest thing, the vertex y, is the function evaluated at x. So you would take this x value that we just got here and insert it in the function, the original function up here that you see. So if I rewrite that, the function evaluated at x equals negative 2 would be equal to x squared plus 4x plus 6. So you would have to put a negative 2 in 2 places. Then follow the order of operations appropriately. In this case, you would do squaring first, naturally, right? This would be positive 4. You would then you would then do this. You would then multiply 4 times negative 2, which would be negative 8. And there's a leftover 6 here. I'm just kind of concisely writing this because my lack of board space here. I don't want to set a bad example. You really should sort of write things out, especially if you feel sketchy about it. 4 minus 8, you should do this first, is negative 4 plus 6. And then negative 4 plus the leftover 6 means that the y is equal to positive 2. Right. So where's the vertex? The vertex is at the location negative 2, positive 2. I could put a dot, thankfully, right now. I'll do that. So here's my coordinate plane once again. the vertex of the parabola is at -2, +2. Let me just remind myself, -2, +2. Yes, okay. Nah. Make sure that lines up correctly. Nah. Just don't matter. I have to shift it because unfortunately I had the whole acrylic plastic not quite where it was supposed to be. Okay. Alright, -2 is x direction, +2 is up. Now see what you have here. Alright, this is the vertex. If it were blooming down like that, and it's not in this case, then there would definitely be x-intercepts. But you could already guess, right, without doing anything else, that there's not going to be x-intercepts, because if it's starting up here, that's the vertex, and the whole thing blooms upward, it's avoiding the x-axis. You can tell that already. Let's say that you aren't sure. Right? There's a couple of other things we could glean here from this information, from these calculations. The vertex x would also be the axis of symmetry. I'm just going to duplicate some information here. If step 3 was we got the vertex and it's at -2, +2, then step 4 would be the axis of symmetry, which would be through x equals -2. Which means if I were a good guy, what I should do is draw a dashed line through this. I'll do that now. I should use a ruler, but I'm gonna skip on that for a moment. And just label this as the axis of symmetry. All right. That would help you if you needed to flesh out the drawing by figuring out one value and then imagining that there's a reflection of it on the opposite side of this axis. Okay, is it faint? It looks like it's visible. Okay. More calculations. Again, we should be suspicious. Blooms up, all right? And we already figured out the vertex is above the x-axis, so unless it was upside down, it's not going to have x-intercepts. All right, but let's say you didn't know. All right. If you went through the process of looking for the x-intercepts, all right, you would do the same thing as normal, which is to say, all right, I'm going to stick a 0 in place of y. So we change the function notation and just call it y. And in that case, it would be 0 is equal to x squared plus 4x plus 6. Right? And since we have experience dealing with quadratic equations, never mind quadratic functions, all right, that is set equal to 0, maybe we could factor it, right? Since it's not too ugly, your intuition would probably tell you, rightly, that, well, if it's a trinomial, it usually factors as a binomial sitting next to a binomial plus or minus, whatever it is. And then you tinker with it, all right, to get to the solution. So you'd say to yourself, well, if it's x squared, it's probably an x here and an x here, all right? If I consider the factors that make 6, it would be 1 and 6, or 2 and 3. All right, thankfully it's a small number, so you don't have to look too much. Do either of these pairs, choice number 1, choice number 2, in any way make it possible to make the number 4? Neither if you added nor subtracted. If you added 2 and 3, you get 5, that's not 4. If you subtracted them, you get 1, that's not 4. If you added these, you get 5 again, not 4. If you, if you add them, you get 7. And if you subtract them, you get 5 again. So it's not going to work, all right? This is not going to factor. This is what you would call prime, right? Cannot be factored. So then a person will go, I'm not taking this line down. I'm gonna whip out the bazooka, all right? With the swat and the fly with a bazooka, which is the quadratic formula, right? Dun dun. And you really shouldn't bother because you're going to get something imaginary in this case, but let's go through the motions just to prove it. Right? If you went for the quadratic formula to figure out x, here's the formula. A. You go back to the model up here and pluck out 1, 4, and 6 and appropriately put them in here. So you'd put a 4 here, and a 4 here, and a 1 here, and a 1 here, and a 6 here. And you'd pay special attention to the discriminant, the inside guts of this radical. 4 squared would be 16. 4 times 1 times 6 would be 24, and then it would subtract, right, because of the minus that's in the formula. Meanwhile, this is all underneath the radical. You would end up with a negative number, right, which is -8, and it's already not real, right? You could go the whole 9 yards if you want. You could say, well, if I have a negative number under a radical, let me just acknowledge that by putting an I out in front to say it's imaginary, right? And then attempt to factor this. You would attempt to factor it into 4 times 2, right? In which case you'd end up with this. You'd get -4 from over here, plus or minus the square root of 4 from this factor is just 2 with an I attached to it because it's imaginary. And then there's the leftover 2 inside, square root of 2. And this is sitting on top of 2 times 1, which would be 2. You could simplify it further. You could say, all right, well, that's 1 fraction, this is a 2nd fraction. That's their common denominator. In which case, the 2 here would cancel and this would reduce. So you'd end up with -2 plus or minus I square root of 2. What can you even do with that? Right? It's imaginary. If you were in a class called complex analysis, right? Or in electrical engineering, I am told anyhow that imaginary numbers are somehow relevant. Perhaps you could attempt to graph this, right? But for our purposes, basically it's dead in the water, all right? If it's not prime, all right, if it can't be factored, all right, you could try the quadratic formula, but if you end up with something that's not real, all right, then there is no x-intercept. Right? You can kind of tell if you started to graph a little bit to begin with because of the orientation of the bloom, right? It's blooming upward, not wilting. Right. Does that mean you're done? No. What you could do is test out the y-intercept next. We need another dot. We only have 1 dot right now, we have a vertex. We have ruled this out. There are no x-intercepts in this particular case. It's not always going to happen, but it happened now. In the case of step 6, the y-intercept, it's the same process. Right? We're going to stick a 0, but we're going to put it in a different location. We're going to put it in x. That's going to be super easy, right? We just got to stick with the labeling of y. Y, rather than function notation, all right, is equal to x squared plus 4x plus 6. And then super easy, stick a 0 in place of the x's. 0 here, 0 here. Go through the order of operations. You square first, that's 0. Multiply second, that's 0. Plus 6. And now you have this. Y is equal to positive 6. Therefore, the y-intercept is at the location 0 for our x input and then 6 for our y output. I'm going to put a dot at that location now. Don't go away. Okay. If I go to the origin, as I always should, right? 0 is neither left nor right, stay put, but positive 6 is up. 1, 2, 3, 4, 5, 6. You have a dot here. Okay. Now, since we need a minimum of really 3 dots in order to draw a satisfying parabola, now we could take advantage of the axis of symmetry. How far away from this location is the axis of symmetry? All right, 2. All right, and we know that it's not blooming like this. We know that we have this so far. All right, blooming upward, and it goes through that point, and that's the vertex. This is a y int. We could make a guess then, an educated guess, which is correct, all right? Which is that if the distance from the axis here to the axis of symmetry is 2 blocks, then there should in theory be another point here. That's the mirror image of this y-intercept. So we'd have the rest of the picture. And there you have it. Okay, your parabola. Okay. All right. Now let me show you something. There's this sheet. You're going to do this by a calculator, which again, no sin in that, it's a skill. All right. I tried to summarize here. All right. This is primarily the course that you will go through. Hit the y equals button and then press graph. This is assuming everything goes according to plan. If you had something that involved an inequality, or in theory, if you wanted to graph even x for the sake of an axis of symmetry, it's a vertical line, remember x equals whatever number, you could go through this key sequence, at least if the software is updated. The only problem with this is that a lot of times you have to go back and intentionally turn it off, all right, because it might make your future graphing a little bit problematic. You would press app, scroll down the list to where it says in equals, and then hit graph, right? And you'll see some options. Right. I don't like to do it myself, right? But I'll show you. Let me turn on my calculator first. I have a TI-84 Plus, right? And I want to say the Plus is the thing that has the apps. This is a little tedious because it's slow. But if you go down here, there's some games in here incidentally as well. Like Block Dude, it's a fun game. Is that it? Espanol, no. Français, okay. Fun Science. Okay, in equals, here we go. And then you would press enter. And then you see this nice opening title screen here. And now you have, I had something in here apparently at one point. Oh, let me clear that out. All right. A couple of things. You notice up in the corner, no, we fudged it. There is X suddenly, right? If you wanted to, if you scroll up here, you could in theory draw vertical lines, right? So let's just say that you notice that there are these features that show up along the edge of the screen here. The function keys across the edge engage that picture of a function key, this one, this one, or this one. That would work for the y's as well. It normally would appear there. Let's just say that you just went with x equals to get an axis of symmetry in. It's not going to be dashed, all right, unfortunately, but so be it. Where did I have it at? -2, right? So I can put it in here. And now if I hit graph, it graphs vertical lines, right, in the appropriate place. This is meant to simulate an axis of symmetry if you wanted one, right? It's kind of overkill. If you wanted to just graph the regular function, then you can go back to, notice that this X is highlighted. It means that something is drawing for that purpose. You could now switch this out to an inequality symbol. I wouldn't want to do that. I'm going to leave it as an equals, right? And then type in the function we just had. So in theory, if I typed in x squared plus 4x plus 6, you can superimpose these pictures, right? Hit graph. There's an error here somehow. I suspect the zoom is kind of messed up somehow, so I'm going to go ahead and fix this. There's two choices you have. You can go with Z standard. That's usually a good bet to try that first. That looks more normal. And there's the axis of symmetry. Right? Notice where the vertex would be. If you wanted to, all right, there's a lot of things that you could get just from kind of staring at the drawing, but you could, for the sake of precision, make the calculator tell you. If you hit trace and you're suspicious about any point, you could enter an x value, press enter, and then it would tell you. Like, for example, if you said, well, what if x was 0? All right, then it will tell you logically that y would have to be 6. That tells you the y-intercept without calling it that. If you wanted to get the vertex, you'd have to go, well, it's a minimum in this case. So you'd hit second and then engage the calc feature, which is behind trace, and then choose minimum. And then you hit enter. And then it asks you these questions, which are a little annoying. You have to basically think of it as a horse. Now, I hate horse racing because I think it's cruel to the animals, all right? But what do they do to horses? They put blinders on them, right? Right? Supposedly so they don't get distracted. Probably so they don't realize that they're in a stupid horse race. Anyhow, that's to focus, all right? Basically, your calculator, you have to tell it where to look, all right? So when it asks you left bound or right bound, you have to kind of scroll over to where, just very near where you think the vertex would be. All right, so just like right on top of it, if you can help it. All right, that is as far to the left bound, as you want it to look. Very narrow. The narrower, the better. All right, and then just to the right of that, right bound. All right, then I'll just hit enter again. And then it says, you want me to guess? And you go, yeah, that's the whole point of this exercise. And then it tells you, this is the minimum, -2, 2. That's the vertex. It's just being referred to as a minimum. All right. Okay. I'm gonna probably have to turn off my app. So if if it gets cumbersome, sometimes you have too many pictures superimposed on one another. Do go back to app, scroll down to in equals, and turn it off. It's a little annoying, but you can get to it. There it is. And quit. And now you're free. Notice when you hit y equals, there's no x in the corner anymore. Okay? And if you hit graph, it would just be the parabola without that line. Okay?
I don't know why I took my glasses off. I'm taking my vision off.
Here's also what you can do. If you're looking for the y-intercept, all right, in theory you should be able to get the x-intercept, but I've had mixed luck with that. Right? If you're looking for the y-intercept, if you hit second in graph, it engages the table. It shows you a list of inputs and outputs, y's and x's, x's and y's. Look for the 0 in the y column, right? And then read what the x would be equivalent to. That's very good for the y-intercept specifically. In theory, it would work for x, but I have had mixed luck with that. If you want to get the x-intercepts, this is probably more straightforward. Hit second and then trace to hit calc, and then know that x-intercepts are synonymous with the term zeros. You're gonna have to go through the same process of going, hey, I want you to look here, all right? And in theory, you do this exercise twice because you may have 2 x-intercepts. But it's a way of getting those points without the calculation. Okay, again, as I mentioned, the vertex is the axis of symmetry, or that point of x. You can get that if you understand that you're dealing with a minimum or a maximum. And you can only tell if you draw the picture somewhat to begin with, unless you're paying attention to what the sign is of A. Okay, that's useful. Right, so I'll have that handy. Again, this is also good for domains and ranges. All right. Let me get rid of this. Kind of a lovely thing, the calculator, you know. Think about it this way. Biology class, right? The biologist uses a microscope to analyze things. A math person, or a math student, whatever, right? All math people, right? Our microscope is a calculator. And that's a nifty one. All right. All right. Now, let's say that you had to write an equation from scratch. So let me show you a method for that. Time check. Yes. Okay. All right. Suppose you're given a picture. All right. Given a graph. Write an equation. Write a function. A quadratic function. So I'm going to draw a very simple picture. And I'm going to try to do this as fine as I can without the use of grid lines, which is probably stupid of me, but I'll finagle it. Okay, if you have a graph that looks no more complicated than this, and have a couple of features here. Let's see this as well. Something like so. You have all the essential if you had to write an equation from scratch. I don't think that's going to come up, but it's still useful. You have a better understanding of it if you know. Right. Let's learn how to read what the key features are. All right. First of all, this is apparently this is a parabola, right? So what does that mean? It means that it's going to be a quadratic function, which means that the degree is going to be x2. Right. Happens to be blooming upward rather than wilting downward. Blooms up. So the a value would have to be positive, whatever the a is, right? There's some other key features here. There's a vertex. It's a little hard because I drew it not on graph paper, but if you can imagine this is an increment of -1, and this is an increment of -2, and this is an increment of 1, 2, 3. This vertex would probably be the location of -2, -3. Notice that the picture, the graph, goes through the y-axis at one point, and nicely it's right on a grid line. So you could get the y-intercept from this. And the y-intercept would be 0 naturally for the x, and it would be apparently -1 for the y value. What is slightly a little more complicated, not a horrible, is that there are in fact two x-intercepts. There's an x-intercept here and an x-intercept here, and neither of them is on an exact grid line. They're kind of in between. So if you would guess in the x dimension that this is 0 and this is 1, and that's about halfway, then you would reasonably say to yourself, well, it's about +1/2, and then it would be 0 for the y naturally because it's an intercept, right? As for this one, again, if it's somewhere in between these two increments, 1, 2, 3, 4, 5, then this would be -4.5, 0, right? That is everything that you could glean out of a picture like that. That's just reading the drawing. X-intercepts, Y-intercepts, and a balloon. All right, and if you really wanted to, right, you could draw an axis of symmetry and then predict other features. All right. Hoping that ideally they'll land on a grid line. All right. I probably should have drawn on a graph, but I'm trying to pace myself a little bit better. Anyhow, let us say that you start with this model. The f of x is equal to a plus or minus x minus h squared plus k. This is probably the easiest one to go through because already we have a vertex, so we can fill in those features. And then it's just a matter of figuring out a rather than a b and anything else. So this is probably easiest. In theory, you could use the intercept form because we have actually already bothered to predict the x-intercepts, right? It's just that they're fractions. So they're not warm fuzzy numbers to work with, they're not impossible, but they're kind of annoying, right? You would rather have a whole number, an integer, right? So we know for certain, because of the orientation of the balloon here rather than the wilt, that this is a positive. So I can fill in that much, right? Let me put in these numbers, -2 and -3. This is an h value and this is a k value. Do include the sign. This is the model, right? And I'm going to put a -2 in here in place of our h, right? And I'm going to put a -3 here. I'm going to change this to just regular ordinary y for right now. So what do I have? I have y is equal to a, positive, x, a double negative is +2, squared, -3. Now, to find a, right, would be the next thing. To find a, use any point that is part of this graph. Okay? What to me would probably be the best thing to do, because the numbers involved are usually pretty small, is go straight for the y-intercept. Right? You could stick a 0 in place of y immediately, right? And then you could stick a negative, pardon me, you could put a -1 here and a 0 in place of the x. Right? That'll make the math involved much simpler. So I'm going to do that here. Y equals a x plus 2. I'm just duplicating this just to show you how I would slip it in. If I use the y-intercept, all right, I would have -1 to put in place of my y, and I would have 0 to put in place of my x. That means that the only letter remaining is the a, so we can definitely rearrange this to solve a. I need this space, so I'm going to erase a little bit. Alright, so if I have -1 is equal to a, 0 plus 2 is just 2 squared still, -3 will simplify. Ever slowly we will inch towards the most concise algorithm level here. So I'm going to have my choice between multiplying and squaring. I really should square. So I have a to the 4, a times 4 rather, -3, and this is still -1. The more typical, better etiquette way of writing a coefficient would be in the front. So I would write this as 4a -3, and this is -1. I like that a little bit closer. And now I'm going to rearrange the parts. So I'm going to move 3 from where it is over here by adding. 4a is left behind. This is one of each sign, so I'm going to subtract them. That will establish a digit of 2, and it takes the sign of the larger one, which would be positive. Right? And now I'm going to divide by 4 to move the 4, and I should simplify the fraction. The fraction would be equal to positive 1/2. Remember what this is signifying. A, in the context of transformations, right, is a vertical stretch or compression. Right? Now, somewhat ironically, right, when you see a whole number digit like 2, you would go, oh, that would make things bigger, right? In the context of vertical, it makes things more narrow, actually. So when you see a fraction in your A, vertical stretch or compression, it's actually a compression, which means that it's going to be wider than normal, the parabola. All right, and that is a pretty wide parabola. Okay, now I'm going to fit it back into the equation insofar as we have it. I need the space, so I'm going to erase this. All right. We have the function of x is equal to a times x plus 2 squared minus 3. All right. And we just calculated what the a would be in theory, and it would be a factor of 1/2. This is the answer. This is the equation in the standard form of a quadratic equation, a function, I should say. Okay. 1/2 times the quantity x plus 2 squared minus 3. Negative 2, remember it's counterintuitive. Negative 3 is the vertex, right? Having this factor here makes the parabola wider than it would normally be. And this 2 makes it a parabola. Now, let's say you had to convert from one form to the other. If you had to convert from, let's say, standard form, which is what we just had, to general, that gets asked of you sometimes. Basically, what is that going to entail? It's going to entail foiling, distributing essentially, or distributing in the normal sense. Foiling is distributing, but if you're just distributing one thing, perhaps after the fact. And simplifying. And green is suddenly writing better at the end of the board. I don't know why. I'm gonna put a little thought cloud here. All right. Alright, that's the process. Let's take this gold and give it a chance. All we are saying is give green a chance. Okay, here's that last problem. Alright, we wrote the equation. Alright, 1/2 x plus 2 squared minus 3. Alright. If you wanted to change its appearance from the standard form of a quadratic function, then it would, and to a general form of a quadratic function, here's what we would do. It's more or less just simplifying it. It's doing the actual intricate multiplication and adding and subtracting. Right? If you had your choice between multiplying something, as this factor of 1/2 would indicate, or squaring, or subtracting, which is technically the most important thing of those three choices? Squaring. Now it just so happens that what's going to happen every single time when you square a binomial, as this is, it's going to produce the perfect square trinomial. from a while ago, I don't know if you remember, so I'll just sort of point at it right now. From our list of different methods of factoring, this old handout, there is a page in here, it's buried, like this. The perfect square trinomial is something that you usually start with it, and then you factor it. What's happening here is that you're going to get something that is going to produce that. It's sort of going backwards, if you will. If you start out with something that is squared, it has two identical binomial factors. Now, in theory, there could be the negative incarnation of this or the positive incarnation of this. But the bottom line is that it's going to be the two outside features, A and B, whatever they are, squared, and then the middle is twice the outsides. Okay? If you have pluses, it's all pluses. If you have a minus, it's just a minus in the front. Okay? So what's going to happen here, right? You could, if you want to, no sin in this, expand it, all right, and do the foiling. That's why I say that's foiled, all right? X times X, X times 2, 2 times X, 2 times 2, right? Or if you have this memorized, you can say to yourself, well, this is going to produce a perfect square trinomial, so it's going to be X squared and 2 squared, and the middle will be twice the outside things. It just coincidentally happens to be one of the outside things is also a 2, right? And if there's a plus in between, everything is plus. It's a little bit faster, right? If you did it this way, I would never fooled you. X times X is X squared. It's just being very careful, so that's a good thing. 2 times X is 2X. X times 2 is 2X. 2 times 2 is 4. The junk in the middle is 4X, all right? That's what this is. It's twice the outsides. So what do you have? You have a half, hang on here, times, I should put this in parentheses, and then minus 3 is still here. So if it's X squared plus 4X plus 4, what I must do now, if I follow the order of operations, and I should, right, is distribute the half to each of these contents. That's the distributing part of this. All right. That's foiling is truly distributing, but it's distributing a binomial to a binomial. This is more or less the distributed property, which is to say, if there's a factor on the outside, each of the contents inside the parentheses would be affected by that. So 1/2 X squared would be the lead term here. What's 1/2 of 4? It's just coincidentally the same number from before, 2. Right, with an X attached to it. What again is half of 4? 2. And then there's this guy still hanging on here. All right. What you end up with is some like terms, the 2 and the 3. These can be merged. So your function in the general form would look like this. It would be the 1/2 as before. No, not a coincidence there. X squared plus 2X minus 1. Doesn't look the same, produces the exact same picture. And if you don't believe me, what you could do is type this as you see it into your graphing calculator, then type this, the same thing underneath it, and superimpose the pictures. There will be no distinction if you do that. There shouldn't, because they're just one style of writing it versus another. That's going from standard to general. Now let me say this. If you were going to go the other way, I'm going to put this like so. If you were going from general to standard, this is also possible. It's a bit more involved though. I need to erase this, so humor me. I need to get a sip of water because I'm getting dry. I'll be right back. Some water.
not vodka, I swear. You know, never teach one inebriated. That would be a bad course of action. If I start scarring my, you know, then you know I'm lying, but I'm not. Okay. We gotta keep the felt out of that. Believe it or not, these markers, they produce a lot of airborne debris, you know. That's why I'm choking half the time when I'm doing this. Anyhow, if you want to go through this thought process, there's two methods. Summarize. Alright. You could go through formulas, which I would do. Or you could go through some kind of procedures. Both of these would work. This is definitely the harder of the two choices. Right? Here are the formulas. Right? First of all, as you can see in that last problem, that A is A, no matter what. Okay? Secondly, if you're looking for an X value, or rather if you're looking for an H value, because the standard form requires that, the H is really the vertex X, which is equal to negative B over 2A. And if you want to get the K value, I'll put this in black. The K value is the vertex Y, right, which is really the function evaluated at X. So whatever this is, you're going to insert in the function. It's 3 steps, and the first one is super easy, so I would definitely go this route, just for the sake of the alternative to be aware of it. It's kind of arduous, right? These procedures involve a couple of things. This involves factoring, which is not a bad thing, you know. And then a process called completing the square. That could be a little tricky. All right, you're not responsible for doing that, but if you want to challenge yourself, just realize that that's what the process will be. Okay? Factoring and then completing the square. Completing the square is difficult for the reason that you have to imagine the problem different than the way that it's given to you. You purposely make sort of like voids that you're going to fill in. All right? It's a bit of a pain in the neck. Completing the square, that method is where the quadratic formula is derived. All right? If you had this, ax squared plus bx plus c, right? And you rearranged it, set equal to 0, I believe. If you completed this, first of all, if you attempted to factor this and complete the square would be part of the factoring, all right? You could derive the quadratic formula, all right? It would take you a couple of pages probably, but it's doable. Anyhow, for the sake of time, if you are asked to do this at all, and I'm even suspicious you might not be, all right? Just go through this process. You have formulas that work very nicely. All right, I'll do an example with you. Got to clean this board with alcohol soon. And wash my eraser. Okay. Let us say that you started with this. X is equal to 2x squared plus 4x minus 4. Okay. This is in the general form of a quadratic function. So this is an A, this is a B, and this is a C. Okay? And we are trying to embed this in the model of standard form, which looks very much like transformations again. Which is this, x minus h squared plus k. We really have three voids that we have to fill in. Right? And that is it. And the A value we could glean immediately from the thing. So we're going to put a 2 right there because A is A no matter what. Okay. Now as for the H value, it's really the vertex X, so we're going to get it from this formula. H is equal to X, and that is equal to negative B over 2A. If I slip 4 in here and 2 in place of here for A, then this would be negative 4 sitting on top of positive 4, and that reduced would be negative 1. So I would put my negative 1 in the position of H here. Notice that there's a negative in the formula, right? We do have to be careful about that, of course. All right. Then we're going to borrow this number. And do this. We're going to substitute negative 1 into the original function because k is equal to y, and y is equal to this. The function evaluated at negative 1 in this case. 2x squared plus 4x plus minus 4. Which means I'm going to stick a negative 1 here and a negative 1 here. Square this is just 1 times 2. That would be 2 minus 4 minus 4. Left to right, this is a negative 2 minus 4. A negative and a second negative, when you add, subtract them, would produce a larger negative. Same signs, you add to get the digit, you take the sign of the larger magnitude, which is actually irrelevant in this case, but it's negative 4. So you have 6, right? That means that you would put a negative 6 here, all right? To clean it up, you would have this. 2 times x, double negative is positive, squared plus minus 6. This is the function in blue, written in the style of standard form. Again, just for the sake of proving that this is true, you could go to your calculator, all right, and draw those pictures. I will type in 2x squared plus 4x minus 4. Right, this is how it would be appropriately drawn or typed, entered in this case. You hit graph. I may have to adjust the screen, but we'll see. Here's a parabola. If my calculation is correct, all right, and if it isn't, it isn't. We'll just have to fix it. But to verify, underneath it, draw what is predicted. Enter to the parentheses. 2 parentheses x plus 1 squared minus 6. And it would look like that, right? In theory, when it attempts to draw the second one, there should be no change. If it's off slightly, if you see a blur, that means that there's an error somewhere. Graph. Nope, same picture. Good. Okay. All right, let's discuss domains and ranges, and again, this would be a good resource for domains and ranges. I'm going to try to fit this all on one page. I drew a diagram. Let's see. Domain and range. We're talking about a parabola, basically, because it's quadratic. That's the shape, basically, on the paper. Domain. To to consider, and then there's range to consider. You could figure it out yourself, and I think people tend to talk themselves out of that, but don't. Alright. Here's a good thing to get started. Right? If we're talking about domain, what does domain refer to? It's what x's are possible. Okay. The range, on the other hand, are what y's are possible. Let's consider two drawings. Right? This is quadratic functions produce parabolas. Okay. In theory, you could have a parabola that is oriented like this, more or less the normal situation. Blooming. Or you can have a parabola like this, which is wilting. That's very sad, right? The normal case is going to be that there are arrows and no holes in the picture. That means that there's no domain restriction. Normally what's going to be the case insofar as the domain is concerned is this. The domain is all real numbers. Is sort of that Great Gatsby-esque R, right? Whether it's oriented like this or if it's oriented like this, whether it's shifted over here or shifted someplace else, it's going to be basically all real numbers. Polynomials in general, of which a quadratic is one type, are basically this situation for the domain. The x's can be anything. In a very subtle way, and I know it's kind of annoying to read it. If you're considering this in a one-dimensional fashion, yes, it's a two-dimensional picture, but because this is curved, right? No matter how far to the left you go in terms of x this way, it's just going to get bigger and bigger and bigger and bigger and bigger, right? And no matter how far to the right you go this way, right, it's just going to get bigger and bigger and bigger and bigger and bigger. Right. The same would be true even if you were considering this. Okay? So when you get to the ranges, and I'll draw these pictures, there's one little caveat here. I'm going to draw this because I think it's more interesting. A sort of parabola, sort of shifted slightly, but still blooming. And then another one that's just sort of wilting. Right. Still bloom, still wilted. Because there are vertices, vertexes, I really should say vertices, but I think vertexes is maybe a little bit more intuitive. There is, in other words, there's a minimum and a maximum, respectively. That is going to cause a restriction. Right? Y values are restricted. So there's two situations, and I'll kind of put it above here. I hate to erase this, but I need the space. So if you have something that basically is oriented upward, a bloom, right? then this is the range. Right. It's going to be the y coordinate of the minimum, which is really the vertex. All right. And there'll be a bracket because it will be included unless there's some hole there, and it really shouldn't be. All right. Remember, this is the vertex. In this respect, it's a minimum because of the shape, the orientation of this. Comma, and then the y values increase upwards, so it's going to go to positive infinity. Remember, infinity is not a specific location, so we use a curve in that respect. If you're dealing with this one, the range will be more or less backwards. It could be anything downward into infinity, all right? But there's a maximum here. This is the vertex. We always start with the lower boundary. So if the lower boundary is infinity, it would be negative infinity, comma, the y coordinate of the maximum vertex, which again, bracket because it is included. All right, I hope that that's visible. I write it up here a little bit neater. Y max, comma, positive infinity. This one, negative infinity up to and including, minimum here. Y max. Okay. Notice that this is written in interval notation, whereas the domain a lot of times is written in set builder notation. Now we're going to go do section 5.2. 5.2 is a lot of theory. I'm going to give you a couple of examples because I want you to get your feet wet. Right? But it is a lot of theory. So I try to summarize. Let me start with some terminology. And in that event, I will refer to this extra thing in the packet. Right? There's this page that says polynomial terminology with a word bank. Right? I want to make sure that this is really clear. Okay, let's dissect this. Right? As is often the case in math, there's more than one way to do something, and there may be multiple contexts, right? Which means that the words themselves are ambiguous. Right? So we need to be able to decide what the context is. Right? If you're looking at this thing that I have drawn here, this is section 5.2. Which is about the power function. And polynomial functions. Let us analyze these features. This is actually drawn in black on my handout, so let me just try to simulate that. Okay. There's a blank box that I put here, right? And it's pointing at this digit of 2, right? In the usual context, right? This is what you would refer to as a coefficient. I don't have a lot of space, so I'm going to just write it nicely here. This is a coefficient. Right? The fancy way of saying number sitting in front of letter. Right? It is understood that they're being multiplied. Right? When you get to the actual variable here too, you notice that there's 2 different boxes on the handout. That's because there's two different contexts. Right? You could refer to it from the context of powers, right? Or you could refer to it in the context of it's a letter. So let's start with the more usual one. This is the variable in the usual context of coefficient and letter, you know. But then it is also alternatively from the context of something that has an exponent, a power of x, right? This is a base. Okay. Same thing goes for this 3 here. This has two different contexts. You could refer to it in the context of a power, which is that this is an exponent. But you could also refer to it in the context of the coefficient and the variable, in that it has a degree. Okay? So just realize these two words are appropriate for that feature. These two words are appropriate for this feature, except that they're specifying its more or less job, if you will. And if not to convolute things, but you've heard me use the word power here. All right, this is kind of conflated a lot. People make mistakes when they refer to this. Not a big deal. But if you saw 10 squared, right, or 10 to the second, all right, this entire thing is a power of what? Don't say 2. It's a power of the base, whatever the base is. So it's a power of 10. It's not a power of 2. It's to the second power, right? English sucks when you're teaching math. It's true. Because even the position of the words in the sentence change the meaning of what you're talking about. Anyhow, it's a power of 10 because it's always going to be a power of the base, but alternatively you could refer to it as the second power, right? Why? Because what's the first power? That's the first power of 10, right? Anyhow, I digress. Terminology is important, right? Because it even in a subtle way, it could be telling you which direction to go. Right. Then what you see adjacent to this on the same piece of paper is this. 2, I have a 7 here, and a 3, and a 5. And I put this in black on purpose. X, X. And I put pluses in here so it wasn't too creative. And I put the exponents in red again. So I put this as 2, 1, 1 technically. All right, there's a bunch of boxes here to describe this. You know, I'll point to this piece of paper again so you know I'm not crazy. Let's start with this. There's the context of referring to this by its individual parts, but not specifying any particular one. All right, these things collectively are referred to as terms. All right, anything separated by plus or minus is a term, right? That's a term, that's a term, that's a term, that's a term. All right. The number of terms decides what type of polynomial you have, and we only have sort of a nomenclature up to 3, right? We have monomials, binomials, and we have trinomials, right? That would be 3 terms. Beyond that, they don't go, oh, it's a quadrinomial. That would make total sense, right? Like a bicycle has 2 wheels and a tricycle has 3, so therefore a quadricycle, which would be a car or some ATV, all right, would be a 4-wheeled thing. They don't do that. They just say it's a 4-term wide polynomial. All right. Anyhow, these things in the middle here happen to be like terms, and we care about that because we can simplify if we identify them. Like terms can be added or subtracted. Okay? Now, what qualifies something as a like term? They have to have 2 features in common. They have to have the same letter, basically, the variable,
and they have to have the same exponent, the same degree. And the only thing that you actually pay attention to when you add or subtract them is the digits in the front, really. Maybe the signs, of course, naturally. Anyhow, what is 7 plus 3? 10x, right? And you could put the 1 if you like, but it's more or less an option. Right. The whole thing, if you were to consider it at once, is referred to as a polynomial. Poly as in many, right? There's monotheism and there's polytheism, right? Famously, right? Poly as in many, all right? Let's see. It happens to be in good etiquette. Now there's a little extra box here that I put here, and this is important, right? It's a polynomial, I would write that word here. And then the etiquette is that it is in descending order. That's an N, I swear. Descending order is referring to the degrees as diminishing from largest to out of existence. This technically would be x0. Okay, there's no x there really, but from the perspective of a calculus class, they would think of it as being x0. Right? All right, anyhow, it goes down. This is the preferred. This is pink in the air sipping tea. Good etiquette, if you will, of math. I know that sounds weird, but think about it that way, it's helpful. All right, descending order. When you're asked what the degree of the polynomial is, you want it to be in descending order in order to make that decision. All right. Here's the last thing. This hanger-on over here is best referred to as a constant. Right? How come? Because it has no letter attached to it. It's just a regular ordinary number. Again, from the perspective of a calculus class, we would maybe envision it like that instead. Right? For the sake of performing something called derivatives or integrals. All right, but in pre-calc and in algebra 2, right, you don't really worry about it. Just go, it's the constant, you know. Doesn't have a letter. Okay. Now that the terminology is out of the way, save that information, it's useful. All right, let me give you another diagram to elucidate. Okay. Now, I want to go back to my little drawing that I have done for you before and sort of edit it for our purposes now. We have functions that we're talking about. This is section 5.2. And yes, there are algebraic functions, which is what we're really concerned with. And then there are the polynomial-based functions, which is really what we're obsessed with. Based. All right, again, something that is polynomial-based is based upon this building block. Plus or minus, and there may be several terms. All right? The conditions, again, are these. If it's a polynomial and not rational function or radical function, this exponent has to be non-negative. A non-negative integer, which is code for saying the positives or the zero. Right? It's a whole number. It means a positive or a zero whole. Right? Not a fraction, not a negative. Right? The other condition is that this coefficient has to be real. Right? In order to qualify it as this. And it could just be one term, or it could be several terms plus or minus. Right?
The only other caveat is that, well, I don't think this is super important really, right? A should not be 0. Right. That is technically real, but then it would, it would be nothing. 0 times that would just be 0, right? So you really wouldn't have anything, right? The real distinction between this and the thing we're going to be talking about now, the power function, is that this can be multiple terms, multiple, not multiply, terms wide. Okay, and then these two conditions. There's this other thing which really is difficult to fit into my chart, but I'm going to put it adjacent for the sake of contrast. So let's just say versus, Ready, round 1, fight! All right. There's the power function. Functions, I should say. Which looks remarkably similar. But they're kind of a slimmed down. I'm not drawing a line to connect these because it's not really the same thing. It's just it's kind of an example of this, but you're going to see there's some conditions that stray from the definition of a polynomial. So it's really its own thing. Its own thing. Right. Okay. Now, the key takeaway from this, it's less strict. All right. If a polynomial is based upon this building block, and it's strict in the sense that it has to be a non-negative integer for the exponent, and it has to be a real coefficient that is not 0, it is going to be typically a single term. That is the only real strictness of it. Oh, I smell soup. Something smells nice. Single term only. Alright? But the other conditions are less strict. Right? Alright, so a lot of times what they'll do for the model, instead of having a model that looks like this, they'll tweak it ever so slightly to make it distinct. So it will look like this. I'll put it in blue maybe. A times x, and then I'll just put this p up here instead. I hate that, but here's how it's different. Right. This could be anything. Right. Any real number anywhere. Alright, for that value. A would have been a nicer choice for a lot of perhaps. A isn't anything. Right. The only other condition is that this has to be real too. Right. So it's less strict in that it can be any real number sitting here. Right? But it has to be a single term in order to qualify as a power function. Walk is a dime. Alright, let me give you a couple of examples of what a power function looks like, and you'll see the difference. I'll just draw them adjacent here.
I think I better hit my wood with alcohol.
Let's see. Here are some power functions. They'll start out being basically the same, but let's say you had the function and it was x to the 0, right? That technically qualifies as a polynomial, right? Because you have a non-negative here, and the coefficient is technically 1. Right? A lot of times we just don't bother to write that. In a more simplified way, you would just see this as simply, well, it's 1, That's the outcome, assuming that x itself is not equal to 0. Right? Still technically a polynomial, but it's only one term. Right? if you saw this, the next degree, next second, this is 0th power. Let's say if you saw x to the first, all right? Still a polynomial, right? But it's only one term, so we're going to call it a power function. Same thing here. X squared, right? It's the square function, granted. This is a linear function, or an identity if you like. Still technically a polynomial. But now you're going to see something different, right? What you could see instead, I'll put it here, is being less strict about what sits in this position. A function that is negative. So what do I choose? Let's go with just -1, right? Already we're deviating from the definition of a polynomial. What does this really mean? When you see a negative, this is code for, you better put it down here, buddy. And then it's a reciprocal function. Okay. If you saw, in theory, this, x to the -2, then you would have this instead, x squared. And once you move it, it's no longer considered negative. That negative that is in this is not saying that the value is negative. It's just a notation, all right? It's really a label to indicate that it should be down here. It's a reciprocal. All right? And that's just changing the sign. What if you changed the type of number? What if you had 1/2, right? You probably have some vague awareness already. I mean, I know I alluded to it, that this exponent here, which is not a whole number certainly, it could never be called an integer for that reason, all right, is really the square root of x, right? In theory, you would put a 2 inside this check mark. I don't know if that's out of the frame, I'm sorry. Just going to address that. And the 1 would be here. I'll do another one. If you had a function where you saw x to the 1/3, right? In theory, this is not a non-negative integer, it's a fraction. It's really a radical function. It's a radical function written using rational notation. Or is that a mouthful? So it would, in theory, be that. Okay? In all cases, you see though, one term, one term, one term, one term, one term, one term, it's one term. So these all qualify as simultaneously polynomials and power functions, but only these are strictly power functions, right, for right now. They are technically reciprocal and radical, but don't worry about that, right? These are examples of power functions. Right. Which are kind of cool, right? They're not too complicated, they're just one term. Let me spray this, which is getting bad. I'm sure it's getting bad, so. Do with that, no slipping, no tripping, no slipping. It's very slight, but to me it looks terrible. My eraser, I really got to clean it because it's smearing debris all over the board. Put that up. Caught me red-handed. Hopefully this will help for the immediate lesson. Come on. Sorry for that. Okay.
All right. Let me sort of just explain this handout before I go forward. This has to do with degrees of. This handout is to summarize degree of an individual term, and then there's degree of the entire polynomial itself. All right. The degree of this this is noticed in descending order. All right, it goes from 3 to 2 to 1 to 0 technically. The degree of this is just its exponent, so it's 3. The degree here is just 2, this is 1, and this would be 0. All right. So maybe fit them in like this if you wanted to fill in the void. All right. 3, 2, 1, 0 would be these. When you're referring to the degree of the entire polynomial, it's the highest available, which is why it's to your advantage to put something in descending order, because then you see that it's 3. So you say the polynomial degree is 3. All right. If you have this weird situation where you have 2 letters simultaneously, normally you would never dare combine these. Right? That's what this box is over here. Right? Bear in mind that the what is that? Adding the exponents in this case merely for the purpose to identify degree is not the same thing as what is known as the product rule, right? This is more for a theoretical reason, not for an actual arithmetic or algebraic reason, all right? That would be the product rule, all right? This is, you were going to add these to simply decide what the degree of this term is, right? The degree of this term would be 4, right? The degree of this term would be 3. The degree of this one would be 2, and this one would be coincidentally 0 again. All right. So again, you're filling in this portion of the sheet just for reference. This is 4, just for that theoretical reason, 3, 2, 0. And the degree of the polynomial will be the highest available. All right. It would technically be 4. Okay. Now let me draw another diagram, right. Since we're on the subject of degree anyhow. See what my time is, my 2 hours, okay. Let's discuss degree. Okay. Degree of power functions. They'll be similar to polynomials, they'll be even degree. And they'll be odd. Insofar as the drawings are concerned, here's what the effect will be. It's interesting. If you had a simple, the most basic version of a power function, one of the more basic. Just make that a little bit fainter. Less faint. That's a bit straighter, I hope. If you had something like this, I'm even going to go for the regular notation. Y equals x squared. Simple square function. No extra features. This is a power function, technically. All right. It would famously go through 0, 0, and through the point 1, 1, and the point -1, 1, and you'd have the parabola shape because of the degree, like that. These points would be relevant, right? Those 3 are the minimum. If we went 1 even degree higher, what's the next even number after 2? 4, right? You're going to get the same shape basically, but it's going to have one distinction. It's going to be flatter in some way. All right? It will go through the exact same points, but it's going to creep down like that. Not as drastically as I've drawn it, but I'm hoping that it's visible.
They will go through the points similarly, 1, 1, -1, 1, and 0, 0. But it's going to be flat towards the bottom, flatter over here. And it will be like that into infinity. If you did x6, it's going to get even more squat, you know? So be it. If you had the most interesting, most basic simultaneously, odd power function would be something like this. Y equals x to the third, right? That's the staying alive, right? Or you might say the parabola with stroke. You know, it goes through these points. 0, 0, 1, 1, -1, -1. Sorry. So you'd have a picture that basically looks like this, and it looks like the John Travolta Saturday Night Fever staying alive, you know, gesture. To be more nice about it. Right. Anyhow, there's a similar effect if you went the next highest degree, right? So you went to, say, x to the 5th. I'll put this in blue just not to make it too much trouble here. 5. It is going to go through those same points, but as it goes past this and to the origin, it'll get flatter. Right? It gets flatter. Remember what I said. You could test this out. Right? You may have to adjust again the screen dimensions, but like a biologist has a microscope, a math person has a calculator, we can examine the fine details with this. Okay. Right. This is a discussion of degree, right, and its effects. It's very theoretical, as you can see. Right. Let's discuss end behavior. It has to do with the arrows. Blue is being in trouble now. End behavior has to basically do with the arrows. And there's something you could do, which I hope this cooperates, but something called leading coefficient. This is why the word is important to know. Leading coefficient tests. Alright, so when we're talking about the leading coefficient, right, that is the one in the very front, right? Just to generalize, I'm going to call it A, and I'll make it a positive situation. And then I'll try to fit it. I don't know if it's going to work, but I will try. Alright, maybe on the paper if you're writing this, alright, just leave a little bit of space and then put negative A. It'll still have these other features, X, and whatever this N is, X and whatever this N is. But we want to consider what happens when you just change the lead coefficient from a positive to a negative. Okay. We will consider how it affects even degree problems. Even degree power functions. And how it affects odd degree. So I'm going to try to limit the left side just for evens strictly, and the right side for odd at the plane as well. Try to make that a bit straighter. Now, here's more or less how the picture would look in the even situation when you have an even degree and a positive lead coefficient. All right, I'll go back to the example that I had used before. All right. If it was something no more complicated than y equals x squared, it's even, and the lead coefficient would technically be what? Positive 1, right? In terms of the arrows, the end behavior, where are the arrows pointing? The arrows are pointing up. That's the end behavior. Okay. If I had the same situation, the same function with one change, make a negative. Here's the drawing. Instead of blooming, what's going to happen? It's going to wilt, right? So this is just this one ever so slight alteration. Still squared, still an even degree. But let's just make this a negative. Right? You can put a 1 if you like. Where are the arrows in this instance? The arrows are pointing down. Both of them. Let's take the odd situation now, right? I'm gonna try to squeeze this in here. Right. This one's a little bit weirder because of the droopy nature of it to begin with. Taking the example from before, the most basic case really, x3, it's an odd degree. Let us say that we throw in, again, technically it's positive and we don't bother to write 1, but it would be. It's going to be just as we predicted. It'll be oriented like that. Alright, staying alive, staying alive. Okay. Staying alive. I can't really do the Bee Gees. Staying alive. Nobody likes my jokes, I'm sorry. And there's no one here to enjoy them. It's me. I'm hallucinating a class right now. All right, that's what we already had established from before, right? What would happen if you just put in a negative coefficient, right? In other words, what would happen if you did this? Very minute change, right? Y equals, this is still x3, still odd degree. But I purposely put in a negative here. Technically it would be 1. It would be, you remember from transformations, all right? The A feature is going to be the vertical stretch, really, all right? But if you have a negative in front of it, the sign as well as the digit, that causes vertical reflection. So what you would have is, I'm going to very faintly draw the original picture like this, but just to walk you through it. This point that would be up here, the arrow here, would instead be reflected vertically that way. And this point that would be the arrow there would be vertically reflected that way. So what you would end up with is a picture that looks like this instead. So I don't have a lot of space to boogie, you know, but it would be from going like this to going like that, you know. Oh, my hip just actually popped back in the joint, that's great. Yay, hips. Yay, chiropractic. Okay. All right, anyhow. So it's just a vertical reflection is really what's happening. All right. Now, there's a summary for this, and I think it's better to explain it now, right, having seen the illustrations. Right? I'm going to draw some sort of notations here, and if I have to, I'll erase this and put them here and here, all right? Just to summarize everything, right? You come across this in a textbook sometimes, and because it's a shorthand notation, it's kind of hard to know what it's talking about, so I'm gonna put some English vernacular in it, all right? In this situation, all right, to summarize, in summary, as x approaches approach is usually what this arrow is meaning. It's never this long, but approaches positive infinity. Right? What is true about y? Right? Look at the arrows. Would you say that the arrows for the y values, right, are going to negative infinity or to positive infinity if there's arrows here, and there really should be arrows? That will also go to positive infinity. Right? As x goes to positive infinity, then the y values also go to positive infinity. Just beware, they have a tendency to not call it y, to call it the function of x instead, but it means the same thing. This is y. This is really y by another name. I'll just put a little thought cloud. I'm y. Right? Okay. If you considered now the negative x's, right? X as it goes to negative infinity, what would also be true of the y values? Do they go to negative infinity? Look where the arrows are pointing. It goes to positive infinity in spite of that. This is a summary of what the x's are doing. As x approaches positive infinity, that is basically x going this way, the y values go up. But even as x goes that way, the y's go up. In this situation, we turn it on its head a bit, so I'm unfortunately going to have to erase this, because I need the space. So I'll just try to erase this much. In this case, as x goes to positive infinity, look at the arrows. The y values, the function of x, goes to negative infinity. Because why? The end behavior, the arrows are going down. Okay? If on the other hand, you say this, as x goes to negative infinity, that's going in this direction, x, y is going down. Negative infinity. In this instance, whether you have a positive x value, right, or a negative x value, you're going to get negative y's because it's oriented like so. Right. In this case, you kind of get one of each. You know? So look what happens. Right. As x goes to positive infinity, the y values go to positive infinity. However, as x goes to negative infinity, the y's go to negative infinity. That's because it's drooping on this side. Notice where the arrows are. This one is up, this one is down. Right? In this case, this one is up, and this one is down. They reverse. It's a bit taxing, right? One more, and then we'll move on. Erase this because I need the space. There is a line here to separate out what we're doing. Okay. In this scenario, as x goes to positive infinity, and you're really looking at this side because this would be x is going to positive infinity here, y is going down. See, the function of x goes to negative infinity. Right. And in this situation, as x goes to negative infinity, that's really x headed this way. Notice what the y's are doing. The function is going to positive infinity, reversed, right? Whether there are additional terms or not, the lead coefficient has the strongest bearing on the illustration, right? There may be several terms, like if you had a polynomial, which would be a power function and then extra parts. That lead coefficient will always have the end behavior, right, zeroed out, right? The end behavior is decided by the lead coefficient, right? End behavior decided, right, by the leading coefficient, right? Even if there are extra terms. You might see some funny dip in your drawing, right? And you can verify with your calculator, but the arrows, the infinities basically would be in these situations. Okay. I tend to draw the same graph a lot, pardon me, the same diagram on purpose, because I'm hoping after a while it sort of becomes intuitive to you. You know how in advertising they barrage you, especially like the insurance companies, they'll just keep saying the same damn lie to you over and over again. Go like 15 minutes will save you 15% of your car insurance, which is a bold-faced lie. All right, why do they tell you so often? Because they're trying to brainwash you. All right. Well, if you're a teacher, your job is to brainwash people for a constructive reason, which is to, get them to remember some facts. All right. Anyhow, I drew this a while ago, and I feel compelled to do it again. So let me do that right now, and I'm almost done. Okay. Here are some features of a graph. I'm gonna keep doing this. I promise you. All right. Because we deal with transformations throughout the semester. That's really what pre-calc is. Already, we have this pretty much squared away. We have the basic sketch of a graph. Right. What is that decided by? Right. I might modify my drawing. This is decided basically by the degree, right? Which is, what is that exponent? I just alluded to, and I sort of mentioned this earlier, there's behaviors, right? But there's two types. I may need this space, so I'm going to do this a little bit more angular like that. Forgive me. Okay. We have behaviors to consider. Right. Behaviors that are the type we just talked about, which is the end behaviors. Basically decide the orientation of the arrows. And it's decided by itself. The arrows are by, this is dependent upon the lead coefficient, as I mentioned. Right, whether it's even or odd. Well, let me just mention this. Whether it's a positive or it's a negative A, and then whether it's an even degree or an odd degree. That's a mouthful, sorry. Yeah. We have a basic sketch, right, which again is dependent upon whatever is sitting here. All right, and then we have the end behaviors, which is the orientation of the arrows, up, down, which is really dependent upon two things, whether it's even or odd degree and what the lead coefficients are. All right. Then there's local behavior. And you're already familiar with this too. Local behavior is more commonly, put this in green maybe, the intercepts but then it could also be something else you'll see momentarily known as turning points. A lot of this stuff was relevant more so before the advent of the graphing calculator, because you'd have to try to sketch something, you know, feeling around in the dark a bit more. So there's techniques here. All right. The x-intercepts are one type. They're easy to get, right? And then there's similarly the y-intercepts. And there's usually just one. And that event you already know. How do you get the x-intercept? You stick 0 in place of y. Right? How do you get a y-intercept? You stick 0 in place of x. Right? And then you do the calculations involved. There's a formula that I want to give you, which I'm going to have to erase some of the stuff above this, just because I don't have the board space. But let me complete this thought over here first. Right? In terms of the turning points, a different type of local behavior, what that really amounts to is minima and maxima. Mins and maxes. Now, and if we're talking about a parabola, what does that mean? A vertex, really. It's not always the case of a vertex because we're not always dealing with a parabola, but for our purposes, it has been. Vertices. And that would be the correct pluralization of that instead of vertexes. Okay. All right. Now, one more thing, and then I'll give you those two formulas that I'm going to look for these here and here. It's not really a fully formed idea yet, so I'm not going to attach it to this picture, but I want to put it adjacent. So I'm going to draw this sort of thought cloud, all right, next to it. All right. When we speak of either polynomial or power function, right? There's two features that we would hope for, right? They have smoothness and continuity. Continuousness is another way of saying that. I think continuity sounds better personally, but that's continuousness. If we're going to stick with smoothness, it's now smootheninity, right? Right. It should be, I guess, right? We should invent that word. Smootheninity. All right. Anyhow, what is smoothness? It means that there's no sharp corners. Okay? So like if you had something like, the absolute value function, I don't want to put it there. I'll erase it a little bit. If you had something that looked like this, a parabola, in spite of the fact that it does have a vertex, it's considered a smooth curve. Right? Even though it has a vertex. If you had something by contrast, the absolute value function, which is the V shape, all right, this is not smooth. This is not curved. Okay. It's not curved. Okay. Smoothness, a parabola comes from what? Square function minimally. All right. We would say quadratic, really. All right. But even in spite of the fact that it comes to a point, all right, it's a curve to that point, almost infinitesimally tiny. All right. As for continuity, that's much easier. All right, what does that mean? It means no holes. Right? When we were dealing with piecemeal functions, right? We had some pictures that were still classic. The whole thing, the piecemeal function, was considered still a function. It qualified for technical reasons, but it had holes in it. All right. Well, these two types. We want continuity. We don't want holes, right, in the picture. All right. So let me get this out of the way, and let me give you two formulas. All right. I would, if I had the board space, I would put them here and here respectively, but I'm running out of space. So let me give you this. Right, and I'll sort of write it here. All right. There's n, shall we say, is less than or equal to d. And then there is n in a different context is less than or equal to d minus 1. This is good when you're concerned with intercepts. Intercepts, and this is good when you're concerned with turning points. Okay, the context of the letter N is going to change. All right. In this instance, one could make an educated guess. That's really all what this is. Educated guesses. The number, that's n, of x-intercepts, otherwise known as zeros, right, should be at most the degree. There's one way that you could read less than or equal to is at most, right, equal to the degree. I like this context. this is at most, would be less or equal to degree of the polynomial or power function or what have you. All right. In this instance, the n is going to change context. So let's just say n as in the number of turning points will be, again, this is the parlance of the textbook, at most, right? Meaning less than or equal to the degree minus 1. So it's always going to be one thing maximum shy of the degree. Right. The reason that anyone would have bothered with this at any point is before the advent of a calculator, because you used to have to do things by hand. So you would make sort of predictions before you would go with one set of procedures versus another. All right. Anyhow, turning points. What are they? All right. I'll straighten that out. Turning points are points where the function switches from increasing to decreasing or vice versa. Let me just make sure that this is in the frame of the camera. From decreasing to increasing. It's very faint. Let's see if I can get this a little bit darker here. Oh, that makes somewhat better. Vice versa. Looks like blood. The math is bleeding now. Spare the math. All right. The points where the function switches from increasing to decreasing or vice versa. All right. So if you had a graph, just hypothetically, that looked like this. All right, it's increasing the whole way. All right. But if you had a graph, let me get you a better picture, sorry. I need space to write, to think, blah, blah, blah. Okay. Increase like 1 here. If you had a picture like this, let's say hypothetically, I want something more interesting. Something like that. And this looks sinusoidal. This is not algebraic. All right. There may be arrows here and here, but you read from left to right. So if we're reading basically in this orientation, look what's happening. From off the scale to here, this is increasing. All right. That's a dud. Look at that. I better pull that out. Okay. All right. And then after that point, it's decreasing. And then it comes up to another point, and then it's increasing again. That writes so much nicer now. Why? Increasing, going down like a roller coaster, decreasing. And then it shifts again. It's the point at which that shift occurs. Those are known as turning points. All right. What that usually means is a local minimum, all right, or a local maximum. This is a local max. This is a local min. Okay? If it was just a parabola, we would just simply call it, a vertex. And we'd say, well, it could be, if it's oriented like that, the vertex happens to be a minimum. If the vertex, if the parabola was oriented like that, then we would say, well, it happens to be a maximum. Alright, but it's local and relative. Okay? Let me do 2 problems with you and then I'll call it quits. Alright, it'll be a 3-hour video. Oh boy. Okay. I'm going to use those formulas. And I messed up my board again. Time to get a new eraser. We'll clean this one. That's what I really should do. Okay. Let us say that you were just tasked with walk at the right. That looks pretty good. You had to determine the number of zeros. That's often the vague instruction that you get, right? Okay. It's kind of okay. I think it's the part of the board program that I'm writing. All right. Just remember what that means. This is a local behavior, and that really, it's code for saying the x-intercepts. It's not finding them per se, it's just trying to make an educated guess about how many there ought to be. All right. Given this function. Three x to the 10 plus 4x to the 7th minus x to the 4 plus 2x cubed. Now, given this function, determine the number of zeros. Make an educated guess about how many there ought to be. Right? Again, if you weren't using a calculator and you didn't have a graph to draw for, or something to draw for you, you would try to figure out, well, how many should I look for? Right. My phone is making a funny noise. What is this now? I don't know, it's my union. Sorry. Okay. Now, a couple of things. You do want this in descending order. That's considered the best etiquette, so just kind of go with that. All right, and number 2, if it is factored, expand it. Sometimes you get something that's factored, right? Expand. At least to the degree, pun intended, that you need to see what the degree is. All right. All right. So, what is the highest degree is really what the question of the degree is. Out of these choices, 10, 7, 4, and 3, that's the degree of the entire polynomial. So, what does that mean? Well, if we're looking for x-intercepts, we're really just going to refer to this formula, very vague formula. N is a number. Let's see if this green works a little bit better. It's the board, it's just too dirty, I gotta clean it. N is less than or equal to D. Right? If we have decided that D is really 10, all right, then let's make a guess. Right? How many x-intercepts would there probably have to be? Right? At most 10. So it's going to be 10 or something smaller. It's going to be less than or exactly equal to 10. So it's 10 or less x-ints. All right? That, knowing that might spare a person work if they were doing this by hand. Okay? Now, if I had the goal to type that in, right, you'd see a very wavy graph, right? That's kind of another thing that it tells you too. If you have 10 x-intercepts, that means that the graph is constantly penetrating the x-intercept, like a snake, right? Now, if we were concerned with, I didn't ask you that, number of turning points, let's say this is question 1, this is question 2, number of turning points, it would be this formula. N is less than or equal to degree minus 1. So we already decided that the degree is 10. So it's 10 minus 1. 9, right? It would make sense that if a graph keeps snaking back and forth through, lacing through the x-axis, that there's got to be turns in order for it to come backward, right? It will have 9 at most. One more. This will be a little bit more intricate. All right, let's have an instruction here. Given this, function is equal to negative 4x times the quantity x plus 3 times the quantity x minus 4. Okay. Remember what I just got done saying. If we are given this and then we have to determine some local behavior, specifically x-intercepts, and then number of turning points. In this case, I'll figure out what the actual x-intercepts are. Yeah. It's less of a chore for this problem, truly. All right. And I'll, as a good sport, I'll do another thing too. Let's say we do this. Second, third, and first I'll find the y int. Okay. Looking for a y int, it's just sticking 0 in place of x. So if this is realistically y instead of the function, is equal to negative 4x times x plus 3 times x minus 4. And I stick a 0 in place of x. That's going to simplify my life, right? 0 here, 0 here, 0 here. That's 0, that's 0, that's 0. But even if you did the first one, because everything is being multiplied, 0's out entirely. This is 0. So the y int is at 0, 0, the origin. The x int is a little bit more cumbersome, right? We could, if we want to, try to figure out, well, how many would there be, If curious, it would have to be n minus d x ints. And this is more or less a thought of guessing. And we need to know the degree in that case. The degree is disguised, unfortunately, right? Because it's factored. Let's do the little teeny tiny bit of factoring that we would have to. All right? At most, I would distribute x to this. It would produce x squared. And then later on, it would be multiplied with that x. And then it would have x to the third. All right? That's kind of cheating, right? But the degree would be 3. So the number of x-intercepts, 3 at most. Now we could find them. Because it is already in factored form, that will spare us a lot of trouble. So I'll make a little line here and do that. Remember, when you're looking for an x-intercept, what are you doing? You're still using 0, but you're putting 0 in a different location. So you're going to put it in place of y. That means that this would be 0 equals negative 4x times x plus 3 times x minus 4. And since it's already factored, if it's already factored, we're going to use the 0 product rule. Hence zeros, right? So the 0 product rule says what? Maybe this thing by itself is equal to 0 in order for that to be the case. Maybe this thing by itself is equal to 0. Maybe that thing here. Right? This one, very easy, right? Divide by negative 4. 0 divided by almost anything is 0. So if x is 0 and y is 0, there is an x-intercept at 0, 0, which we already technically know because of the y-intercept. It's a coincidental point. When you do this one, you minus 3, cancels, and then x is equal to negative 3. So then there's another one, right? X is negative 3 when y is 0. And then the last one is plus 4, right? Plus 4, x is equal to plus 4. So this point is positive 4, 0. Last thing, if I wanted to figure out the turning points, or at least estimate how many there ought to be, never mind where they're located, because that's, you know, this problem would be problematic and you're not responsible for that. You'd have to make more educated guesses and you don't have enough information yet. If you're looking for the turning points, right, let's say that this is part 3 to this question. Turning points, how many would you predict? Right, it's this formula, d minus 1. We've already established that the degree is probably going to be 3, because it's x times x times x. So if I slip a 3 in here in place of degree, what's 3 minus 1? 2. So 2 at most turning points, which would make sense because if you have 3 x-intercepts, and you definitely do, those are 3 x-intercepts, you're going to have to curve back down, so you're going to have a maximum or a minimum. All right. So let's prove a point. All right. We predict 3 x-intercepts. That's what they are for sure. All right. But we're expecting 2 turning points. So let's make the calculator do that. All right. Gonna clear this out. Clear this out. Start with y equals, and you got yourself a blank y. And now I'm going to enter this, even in the factored form. It doesn't matter if you expand it. Just be careful when you're putting in the coefficient, you know, negative 4, use this button. Negative 4x parentheses, x plus 3 parentheses, then a second one, x minus 4. This minus on the end here is the subtraction symbol instead. This is how it would look, provided I typed it correctly, entered. Now hit graph. I may have to adjust the picture, right, but let's hope for the best. Graph, all right. It's not really a satisfying picture, so we need to back off, right, basically. I would try a couple of things first. Man, let's go with the automatic transmission here, zoom. We'll go to Z standard, 6. This is a 10 by 10 graph. It's even chromier. It's a little bit too bunched. So then we'll try this. You could zoom in, zoom out. I'm gonna try zoom fit. There we go, zoom fit. So it might squash the graph. It's still not satisfying. There's a slight curve here. It's very innocent. Well, slight. Let's do zoom in at this point. It's still kind of crummy. Try it again. No, I don't like that either. If I have to do manual, I will. Let me try Z square. Or, you know what I'll do? I'll go back to Z standard. And I'll use zoom now. Ugh. I know I got this to work last time. Let's see, let me try it again. No, that's terrible. Z squared, perhaps. Alright, let me look at my options rather than read them backwards here. Z standard. I hate that. I've done it so often I've actually made my calculator stupefied, so I have to quit. If you ever get your calculator befuddled, you turn it off or take the batteries out of it. It's unfortunately what you have to do. That's correct. Okay. Graph, please. Alright. This is zoom fit. What I'm going to try to do is zoom in on this. I thought I did do that, but maybe I didn't. I may have to do it multiple times. I know that I got it to work. You have to sometimes persist. Oh, you know what I'm doing wrong? I should zoom out. Yeah. Well, I'm not going to waste time. I'll just show you what it would look like. You basically get a picture that looks like this. If you could zoom in appropriately, and sometimes you have to mess around with the calculator until it gives you what you want, you get a picture, just to exaggerate it very drastically, it looks something like this. How do you know? Because you have an x-intercept that is coincidentally a y-intercept, it's that point, right? You have another x-intercept which would be over here, -3, and then you have another x-intercept that would be over here at +4. So, if these are the only x-intercepts, then that would be it. It'd be flying off the page this way, right? And it would be, that's it on this side, it'd be flying off the page this way. Right? Well, what do you have simultaneously? You have a turning point and a second turning point in order to go back down to the x-intercept. Increasing, back to decreasing. We really read to left to right. This is decreasing and that's increasing. That's what the picture would be if I could just get it to zero in on it, but unfortunately I can't. Anyhow, that's it for today. Thank you for sticking with me for 3 hours. For homework, just try sections 5-1 and 5-2 practice in my open math in mom. Alright, for next, when is today? Today's Thursday? By next Thursday. Thursday morning, ideally. Okay? Take care, folks. Be careful out there.